Okay. Thank you. I'd like to begin by thanking the organizers for this fascinating conference, especially Meng Chuan for both conference and two talks, fascinating talks. The title of my talk is supposed to be a joke about baseball, but really I know nothing about baseball. This talk is really about controlled effects that can be realized on M5 brains, a single M5 brain, in fact, in strong flux. So let me explain what is a curve pole and what that has to do with M5 brains. So I'm going to define a curve pole as the counterpart of an electromagnetic dipole, but interacting with a two form. An electromagnetic dipole is two endpoints, two charged endpoints interacting with a gauge field. I'm going to think of it as a fixed length dipole. And let's define a curve pole as the analog of that, a string, if you will, but of fixed shape, whose a string C that interacts with the gauge 2 form, B. But I actually want to be in 6D, where my interest is in 6 dimensions, of course, where the electromagnetic duality, sorry, let me say that again. My interest is in 6 dimensions, and the case where B is anti-self-dual. And then self-duality can impose restrictions. The boundary of this, the string has to be both electric and magnetically charged. And so to formulate the theory, it will turn out that we will need to, as a crutch, fill in that C in some surface sigma whose boundary is the string. But I want the bulk of sigma to be inert under the B field. So let me just go back. So I'm going to call the sigma the curve pole surface. Curve pole because instead of 2 points, a dipole, we have a curve. The goal is to construct a supersymmetric second quantized theory of curve poles interacting with the 6-dimensional tensor multiplet that has this anti-self-dual 2 form. So I want a field phi whose quanta, when second quantized, look like this. Fixed shaped curve, but they're allowed to move. Their center of mass is allowed to move. And the curves interact with this anti-self-dual field both electrically and magnetically. And the question is, how do I build a consistent supersymmetric Lagrangian for something like that? So as I said, again, let me stress again, the shape is fixed. It's an external parameter of the theory. And one of the questions I would like to pose is, does supersymmetry impose any restrictions on the shape, the geometrical shape of these curves? Yes. Oh, right. So let me go back to the, yeah, thanks. So these 2 points can be thought of as the boundary of the one ball. And the curve is the boundary of the two ball, sorry, let me say it again. The curve is the boundary of the disk, so in that sense, it's the generalization of that. So the 2 points, in a sense, are a zero exact chain, so to speak. Yeah.
You wouldn't call it a dipole if you put a positronic on both sides.
Oh, that's right, because it would be a non-exact chain. I mean, in that sense, right?
I see.
That's what I mean. So this is contractible, just like these 2 points are contractible in zero. Oh, right. Sorry, I should have drawn the arrow. Oh, I see. Sorry, I see. Sorry, I see what you're asking. Sorry, I woke up at 5 a.m. I've been slow. Yeah, I neglected to draw the curve. It's an oriented curve. Yeah, thank you. Where was I? Yes. So, following Meng Chuan's advice, I'm going to give the gong show. So I'm going to construct an action order by order. I mean, quadratic terms, cubic terms in the fields, quartic terms. I'm going to stop there. And matching to it are supersymmetry transformations, the 0th order one that are linear in the fields. The delta 1 will denote the quadratic in the fields terms and delta 2 cubic in the fields. And I'm going to require that even though the formalism depends on how I fill these curve poles to accommodate the magnetic interactions, I don't want the theory to depend on how I fill these curve poles. So I'm going to kind of require this hollowness principle. The curve poles are supposed to be hollow. And see what these SUSY and hollowness combine, what restrictions do they give. So I'll present explicit formulas up to and including L4. You never know when you say up to, does it include or not include? So it's a stress. And there is this restriction on the shape of the curves that I'll present, imposed by supersymmetry. I don't know if what I'll present is necessary. In fact, what I'll present is definitely not necessary. I can discuss a little bit more about some relaxed conditions, but I don't know if it's, I mean, I know that what I'll present is sufficient conditions. I don't know if they're necessary. Yeah, and as I said, there's a restriction imposed by hollowness. And if the curve pole is planar, that means it can be embedded in R2 inside R6, then both supersymmetry and hollowness hold, at least up to and including 4th order. And the asterisk, I'll explain later what I mean by that. So sort of holds. All of this is going to be at the classical level. I'll mention a little bit some issues with anomalies at the end. And now I want to take some time to discuss. So what does all of this have to do with M5 brains? By the way, when did I start? Was it 10 o'clock or 10? 10 exactly. Oh, that's going to be easy to remember. Thanks. So what does it have to do with M5 brains? Well, so there's a controlled way, I claim, that we can induce these kinds of interactions on an M5 brain. So this is actually, if there's a physical system, physical in 11 dimensions, that has these sort of interactions, and here's how we can construct it. So it is well known that M theory on a small T3 that shrinks to 0 is U dual to M theory on a very large T3. And if you insert an M2 brane perpendicular to the T3, so it's a point inside this 3 torus and extends in 3 transverse directions, not shown here, the duality will map it to a wrapped M5 brane. So if I ask what are the low energy degrees of freedom of this system, well below the Planck scale, the answer is, well, these are the degrees of freedom of an M5 brane wrapped on a large torus. So it's a free hypermultiplet and a free tensor multiplet using 1,0 6-dimensional multiplet terminology. But now let's add another ingredient. So cut the T3 horizontally to the, let's call the bottom the floor. So cut it horizontally to the floor and glue the pieces back together, glue the two things back together with a twist in the 5 transverse directions. There are 5 because 3 directions are taken by the M2 brane, not shown. 3 directions are the T3, and there are 5 more not shown. So there's a spin 5, so glue it back by rotation in the spin 5. Basically fiber the 5 directions. This is a similar setup to the omega deformation. Take that twist to be very small, kind of double scaled. As the volume of the torus shrinks, as the volume shrinks to 0, the twist will also be very small, but in such a way that some combination remains finite. And the question is, so what happens to the low energy degrees of freedom of the system? And I claim that the poor M5 brane is now no longer free. In fact, what used to be the free hypermultiplet is now a curve pole. To see why that is, let's go a little bit into more details. So put axes on the T3. 3, 4, and 5. The twist is in the direction up, in the direction 5, the SO5 twist. It's called the radii of the torus Ri, R3, R4, R5, and the dual R tildes. So the radii under U duality go into some combination known formulas. I mean, the R tildes are known formulas of the R's in such a way that the volume goes into 1 over volume. So the volume of the dual T3 is 1 over the volume of the original T3. Now let's insert the twist. So that, what happened? Oh, turned off. Did I press on it too long? So as I go up in along the T3, let's say that I wrote. So I want to rotate by an angle theta, and let's say that for simplicity, let's take the twist in some plane, say direction 6 and 7 of the transverse directions. So as I go up, I want to rotate before I glue. I mean, as I complete a full circle in direction 5, I want to rotate also by an angle theta in this transverse plane. And let's call the spin in this transverse plane J. So this is completely, did I turn it off somehow? Do you know what happened to it? Let's see. Oh.
Reverse.
Oh, thank you.
So that's trick.
Aha, I see. Okay, thanks. So as I go up. Okay, so let's say it again. So as I go up, as I complete a full circle in direction 5, this is accompanied by a twist in some plane for simplicity. Let's think about a particle that has spin j in that plane. So as it goes around one loop, it picks up a phase proportional to its spin and the angle. And so if I Fourier transform the second quantized field that describes this particle, I'll find that the modes are not integer, but they're shifted by exactly this amount. And so what does that mean in the dual picture? Well, in the dual picture, it means these quanta are Kaluza-Klein states, and they get mapped to M2 branes that wrap the floor, if you will. And so that means that the M2 brane area is no longer quantized in integer units of the floor, but there's an extra non-integer piece. And if I keep that combination finite, I can just adjust theta so that it will be finite, then I get an extra piece of area to M2 branes that's proportional to spin, but it's not quantized, it's kind of a small finite piece. These are the curvepoles. Well, that looks very abstract and maybe suspicious, so let me give another way of thinking about it. The other way of thinking about it is much more heuristic, but I think it's more intuitive. So I can do formally that U duality that I discussed before, and I can get the M5 brane, and the twist translates. So let me just say that the M5 brane, let's say that it's in directions 0 to 5. I'll pick direction 6 and 7 for the twist, transverse to it. Then the twist translates under U duality to a very strong flux that's also accompanied by very strong curvature, so not to be trusted, of course, but still heuristically amusing. In such a strong background, an open M2 brane can venture into the transverse directions, the 6-5 plane, and if it rotates in that transverse plane, the strong flux exerts a magnetic force that is enough to counteract the tension and keep it open. And one can calculate the opening is proportional to the spin, and I can make it quite large, much larger than Planck scale. And this is the curve pole. I have to wiggle it again. Okay. So this is the curve. Oh, it doesn't.
New batteries. New batteries.
Oh,
okay.
So in the meantime, I'll just say, so this is the curve pole surface area. Now this M2 brane will be very massive, but in the multiplate, there are the states that have the lowest R charge, the ones that come from the hypermultiplate, one can check using BPS arguments, stay very light. They open up, but they stay very light. Thank you. So the macroscopic ones are, of course, not the ones that I want to include in my low energy description, but there are light states that opened up to very large area, much larger than Planck scale, and they're the ones that I want to include. So these are some references about, thank you, next one. These are some references about behavior of M5, for instance, in fluxes. Maybe I missed a few, sorry. What was the? Okay, so back to field theory. So what I want to do is start with the free 2-0 tensor multiplate. So let's break it up into the tensor part, the 1,0 tensor part, and the hyper part. The tensor part has this anti-self-dual field with its self-dual part set to 0. And I want the quanta of the hypermultiplate. These fields, I want they would have the R charge that I want, and I want their quanta to be these curve poles. And the question is, what would be the Lagrangian? So this is a controlled deformation of the M5 brane. So the question of what's the Lagrangian? It's a single M5 brane, so it should be answerable. It's an answerable question. So let's see what we can say about it. These, I want their quanta to stay point-like because they will not have any R charge. Okay, so let's take a toy model first. Let's go back to dipoles. And let's see, how do I add particles that are, whose fields whose quanta are dipoles of fixed length to Lagrangian. So L is fixed, it's an external parameter, and phi is the second quantized field of this dipole, and the way to do it is, of course, simple. All I need to do is modify the partial derivative to the covariant derivative that accounts for the two charges, the positive charge at L plus 2 and the negative charge at L minus 2, and just insert that into the action. That's not going to be quite good enough for us because our curve poles are both electric and magnetically charged. So I can't use the dual gauge field in the same breath with the ordinary gauge field. But there's something else we can do, which is we can attach a Wilson line going from the negative to the positive charge. We can pick some fixed path and just multiply the field by this Wilson line to get a gauge invariant field, and then plug that into the covariant derivative. And the covariant derivative is now written entirely in terms of the field strength. It's a simple calculation shows. So I'm going to work with these fields, and that's going to be their covariant derivative. If you will, this is like a poor man's version of a Seiberg-Witten map for this system, converting non-local interactions to gauge invariant ones. And anyway, that's in the jargon of non-commutative geometry, but we can forget about the sentence I just said. So let's go back to the curve pole theory. So let's do a first try. So I have a field that I want to interact with the tensor multiplet. The tensor multiplet is a field strength, anti-self-dual field, and another real scalar field, and fermions. And I want to introduce these fixed shape sigma that is going to be the open surface. And so the step one is to modify the covariant derivative of this up until now free field phi and add to it a piece that goes like that. I'm going to take the two-form field and integrate it along the curve that leaves one free leg, so gives me an effective gauge field. It's constructed non-locally from the 2 form, and that's going to be the gauge field I'm going to use for the covariant derivative. So that looks okay, but it doesn't quite work because the action should only depend on H minus. Otherwise, I couple to the self-dual part and not just the anti-self-dual part. Shouldn't depend on B explicitly. The interactions that I add should not depend on B. I mean, the reason is that if the interactions that I add do depend on B, then these are only electric interactions. So they destroy the anti-self-duality. They're not magnetically equivalent. These interactions should do magnetically the same thing that they should do electrically, and this is only electric coupling. Now, for a free tensor, the self-dual part vanishes. So I can rewrite dB in terms of H minus. I can do the field redefinition that I discussed before. I can integrate times an abelian surface operator along sigma to get this gauge invariant phi tilde. And in terms of this gauge invariant phi tilde, it's not hard to check that the covariant derivative is written in terms of the field strength. And the field strength is H minus, but that's not good enough because I can't just use the equations of motion. It will, again, destroy the self-duality. And moreover, once I add interactions like this one to the system, it is no longer true that H plus is 0. H plus, as it turns out, gets modified by the equations of motion as well. So I'm not going to do it this way. I'm going to do it in a slightly modified way. I'm going to take the field strength. Let me backtrack a little bit. So first I'm going to fill the curve pole by sigma, as I said before. I'm going to take the anti-self-dual field strength, integrate it over the filling, sigma, use that as an effective gauge field, and use that for the covariant derivative. And now I want to ask, so what does supersymmetry imply? Well, the first thing is it's a little bit of a calculation shows that it requires to add an additional term to the effective gauge field that is obtained by integrating the scalar along the curve, the boundary. But if we go to higher orders, supersymmetry requires quartic terms. And it also seems to impose a condition on sigma. I don't know if that condition is necessary, but to cancel the second order variations, I only managed to do it if I impose a condition. So let me now discuss what this condition is, because this was one of my main points. These shapes are not completely arbitrary. To introduce the condition, let's make the following geometrical definition. Given this curve pole sigma, given this surface, open surface sigma, let's define the curve pole integral to be the integral of, so for a given field, that field could be composite. Let's define box of that field to be the integral of that field along the curve pole. So the field kind of centered here. I'm going to draw a curve pole around that point x and then integrate this 2 form. And the anti-curve pole integral to be the same thing with the minus, going the opposite direction. So the condition that supersymmetry seems to require is that if I do a box and then an anti-box, it shouldn't matter if I change the order of the 2 indices. These indices run from 1 to 6. They're anti-symmetric, so they're 2-form indices. So that seems to be the condition. This is a geometric condition on sigma. I should add, the condition is actually slightly weaker, but a little uglier to write. So if somebody's interested, I can write the weaker condition at the end. But this seems a reasonable condition that I want to write here. So what does that condition mean? Well, it's equivalent if I multiply both sides by another field, phi, and integrate. I can then change integration variables to convert the anti-box, to just kind of move it around. So this condition is equivalent to that. that the integral of two curvepole boxes are invariant if I change the order of the indices on the boxes. Boxes, again, are defined just by integrating the field along the surface. And again, I said this is a geometrical condition. This condition will certainly hold if the integrands are equal. So that's a stronger condition than that. And this condition is equivalent to having the curvepole planar. So there is some plane in which the curvepole is embedded. This is easy to see because if that is the case, then these alpha and betas just run over in some coordinates. I can take the plane to be coordinates 1 and 2, and then these alphas and betas are just going to be 1 and 2. They're antisymmetric, so certainly I can exchange 1 and 2, and 1 and 2 are the same index. And it also goes the other way around. So planar curvepoles are certainly satisfy this condition. Oh, sorry, I forgot to mention. So let's call this condition balanced curvepoles. So planar curvepoles are certainly balanced curvepoles. But these are not the only cases. Parity invariant surfaces are also balanced because the minus here doesn't make much of a difference. So what's not balanced? Well, a chair is not balanced. Not because it doesn't have legs, but just because this doesn't happen to be balanced. Ironically, this looks more balanced than a chair with legs, but it's not. Okay, so again, this is a geometrical condition. The actual condition is slightly weaker than that. I'll write it at the end if people are interested. I don't know what's the general shape that satisfies, that is balanced, but I know that these are sufficient conditions. Okay, so now to the action. So I'm going to start with the quadratic action of free fields. I'm only going to write the bosonic terms, but if people are interested, the fermionic terms can be found in the paper. I'm going to start with the free 2,0 tensor multiplet. H is the 3 form associated with the B field. Phi is the scalar superpartner of B. And these are parts of the hypermultiplet where I is a 1, 2 index. It's kind of an R symmetry index. The H splits to self-dual and anti-self-dual components, and the self-dual part is completely inert. It's going to just decouple, and we don't have to think about it anymore as long as we make sure that interactions only involve H minus. Yeah. Yeah, so this is actually in Euclidean. I actually want to be Lorentzian, but the formulas, for some reason, I calculated everything in Euclidean, so there's eyes over the place. Yeah, thank you. Thank you for reminding me to mention that. Okay, so cubic terms. So cubic terms, as I mentioned, I'm going to make an effective gauge field out of a non-local expression that is made from the tensor field and its superpartner integrated along the curvepole surface. Call that V. V is an effective gauge field. It doesn't have, I should say, it doesn't have any. There's no gauge. There are no gauge transformations here because these fields that make up V are gauge invariant fields. So they're physical fields. But I'm just going to add the minimal coupling. That turns out to be supersymmetric at first order. The current is going to be the U1R symmetry current appropriate for the problem. This is its expression in terms of the scalar fields. I, again, runs from 1 to 2. So the phi's have positive charge, the phi bars have negative charge. Okay, so that's pretty simple. And then once I have the first order corrections to the supersymmetry transformations, I can apply them to the cubic terms and see what needs to be added at quartic order. And what works is this expression. So there are 3 terms here. The first is, of course, the missing piece from the minimally coupled scalar. The third term is some coupling between effective meson fields that I construct from the hypermultiplate. So these are quartic terms in quartic non-local couplings of the scalars. And the middle term is a current Fermi-like pre-standard model interaction. And that term, well, it's required by supersymmetry, it comes out of supersymmetry, but it can be explained by, this is exactly what I would get if I asked how do I describe a magnetically coupled curve pole? So I can start with an electrically coupled curve pole, as we basically did, and kind of do the standard dualization prescription. Treat the field as an independent variable at a Lagrange multiplier. We learned from Jacques should not be called an auxiliary field. And integrate, and that term will appear. So that term is there because it describes the residue of the magnetic coupling of the curve pole. That works well with supersymmetry. And I should also add, in fact, there are no extra fermionic terms. If you ask me how do the fermionic terms enter in the quartic interactions, the only correction that needs to be done at this order is just to add the fermionic contribution to the current, to the R symmetry current that I'm using, and that's it. So these are the interactions. But now let's talk about hollowness. So this formalism depended on how I filled the curve pole explicitly, because the curve pole integrals are integrals over the bulk of the curve, but the bulk, as I said, should be inert. So it would be nice if the theory really depended only on the boundary. It would be nice if for two different ways to fill the boundary, the theories are the same. Of course, same is okay up to a field redefinition. So can we find this field redefinition? Well, that is sort of true, and I'll tell you what I mean by sort of. But first, let me tell you why I insist on that by looking again at this toy model of the dipoles, the fundamental dipoles. So here's again a dipole of fixed length L, and it's minimally coupled covariant derivative. And then I mentioned that I can just attach a Wilson line and get this gauge invariant field and formulate the theory in terms of what the covariant derivative conjugates to in terms of the gauge invariant field. And the gauge invariant covariant derivative contains only the gauge invariant field strength. And then there's something suspicious about this, because what if the theory is anomalous? For example, what if these are charges of chiral fermions in 6 dimensions, let's say, or I mean 6 dimensions, so let's say 6 dimensions. I can take the other end to be very far away, in fact, at infinity, where the fields are 0. So this is just a theory, and this is just a theory of gauge field interacting with a chiral fermion in 6D. It's anomalous. Well, you can say I'll have negative and positive charges, but that doesn't help, of course, in 6 dimensions. They both have the same anomaly. The anomaly is proportional to charge to the 4. So this theory is anomalous, but here it's obviously gauge invariant, whereas the anomaly, well, the anomaly is, of course, what will happen is that the formalism, if there is an anomaly, will depend on how I choose the loop from minus to plus. Let me just repeat again. What do I mean by px? So I choose this shape once and for all, and px is just the same shape of curve translated by x to wherever that field is. And if I choose px, if there is an anomaly, then the theory will explicitly depend on how I feel it. Yeah?
Even before you get to anomalies, if you were looking at a magnetic dipole, right? Unless before you impose some charge quantization condition, the round string connecting the two ends of the magnetic dipole is, of course, visible, right? And somewhere here, I mean, until you impose the analog of that charge quantization condition, you expect its hollowness to fail.
Right. Right. So the Dirac string is visible because it's visible in the formalism.
No, it's visible in the sense that charged particles can detect it.
Sure. Why do charged particles? No, if these are two fundamental.
No,
why would the charged particles detect it?
Only if you impose the Dirac quantization.
Oh, I see.
The Dirac string invisible. This sigma is your analog of the Dirac string, and it's only expected to be invisible if you impose the appropriate charge quantization condition.
Yes, good. Thank you. Thank you. Yeah. Yeah. No, I agree. I mean, I think I agree with that because
physical ones, it's not visible.
Yes. Thank you. I mean, that's
invisible. I mean, well,
no.
So maybe one has to think.
The magnetic flux it can be detected. It's called the Boltzmann-Haronoff effect.
Yeah, I mean that's good because so that means that the coefficient here has to be integer.
Right. The charged particles can detect the presence of the solenoid.
Sure.
Yeah. I mean that's good.
That is exactly the same thing as the failure of hollowness.
Right, and it says that means that I would also want the coefficient here to know. I mean, up until now, everything there's something. Thank you. That reminds me of something else that is not in this slide. There is something else suspicious because the coefficient. I mean, I introduced these boxes everywhere. These boxes are the analogs of this integral here. But wherever I have a box, I could just multiply the box by some number. The formalism is just, there's a box in the formalism, so take the box times a number. Why that number, I want it to be an integer. In fact, I want it to be 1 to describe this, what's happening to the M5 brane. And so far, the formalism doesn't know about it because I did everything classically. Yes. So that's another reason why, thank you. So this is absolutely another reason why I would definitely want hollowness, because I want to also be able to set that number to 1, because it might help me with quantum correction. It might preclude quantum corrections.
All I was trying to point, I didn't mean to divert from what we said. It's just that this is something you already see for magnetic dipoles and little four-dimensional theory. Until you impose some Dirac quantization condition, the string connecting them is certainly visible.
Yes. Thank you for reminding me because I forgot to add that to the slides. That is one other important reason why I need the hollowness. So good. So we need hollowness. So let's. I have 10 minutes, right?
Yes.
Thanks. I think I can do it. I hope. So okay. So hollowness means that if I have the curve pole surface, I just draw it here as a line because 3D. I don't know how to draw nice 3D shapes, but if I deform it, let's say that I deform it a little bit, I want the theory to be the same up to a field redefinition. So let's define this psi to be an infinitesimal vector. Let's talk about infinitesimal deformations, and let's take an infinitesimal deformation. And psi is going to be a vector field defined just on sigma, just on the curve pole, that vanishes at the boundary, vanishes at the actual charged part of the loop. And then a quick calculation shows that the delta of the boxes are these expressions. And so let's see what happens to the various terms in the action. Well, that was the effective gauge field. It was an integral of the anti-self-dual 3 form on the curve pole, on the surface, and an integral of the scalar, of the derivative of the scalar on the surface. The second term, that's a total derivative, so that can be converted to an integral on the boundary. So that is obviously hollow, because it only depends on the curve. So the supersymmetric correction is fine. The first term would have been hollow if H was exact, actually. We're working on R6, so exact and closed is the same thing. So it would have been hollow if if the field strength were exact, in which case I again could convert this box to an integral on the boundary, but it's not. I mean, because I've added interactions, there are corrections to d of h minus. I've written it here in ugly tensor form, but there are corrections that are linear in the current. But nevertheless, there are more terms in the action. So here's the whole action bosonic terms that we have. Well, the first three terms are obviously hollow because they don't even contain that box integration. This term is hollow because it's an integral of a total derivative, and so it can be converted in the same way to an integral on the boundary. So the meson terms are hollow. And here are the three terms that are not obviously hollow. There's some part of V that is hollow, but altogether it's not. And so what can we do with these? These are kind of what was induced from the residual magnetic interactions. This was from the minimal coupling. Well, so this is the deformation again. One can find a suitable field redefinition so that the change in these extra terms takes a rather simple form. It looks like that. Of course, it's going to be linear in psi, and what we have here is something that was left from the residual Fermi interaction, current interaction. So what can we say about this term? Well, this is the term again. This, the change in the action with the field redefinition looks like so. It has this Levi-Civita tensor in six vector indices. And while it is not generally zero, if sigma is 3-planar, so meaning if I can embed it inside R3, then in a suitable coordinate system, these indices just take values 1 to 3. So with the Levi-Civita tensor, that's obviously going to be 0. So if sigma, for example, is 2-planar, and I just deform it in the direction of an R3, that's okay. So while this is not exactly what I had hoped for, I think it still shows us that sigma is, in a sense, incorporeal. I don't completely understand what that means, that you're only allowed to deform it in the R3 directions, but it definitely shows that there's nothing physical there at sigma. So I'm just going to leave it as a sort of puzzling thing. Now, again, this is, oh yeah. So I didn't use self-duality here because I don't want to use self-duality in the action because that would impose equations of motion. Yeah, I mean, no, so I would say no. The self-duality is kind of okay, I think, because is not ruined because I only insisted on coupling to H minus. So that means that the equations of motion are still will allow me to say H plus is determined by the other fields. Oh, that I don't know. Oh. I don't know. That I don't know. I mean, this R3 could be in any direction, actually. There's no restriction on in which direction this R3. So I can deform this curve. I mean, say it's two-dimensional. I can deform it in. I can choose any R3 that contains that R2, and I can deform in that way. I mean, this is just what the calculation gave. So I mean, I don't know what that means. Martin? Oh, it is. It did become deformed. I can show. I have extra. I can show it in a minute. I mean, they have extra slides. So you mean the H plus? The H plus is no longer 0, but contains some. Yes, absolutely. That's yeah. But I didn't really use that. I mean, I don't. It kind of seems like this is an effect that came out because the curve pole is both electric and magnetically charged. But I don't know how to synthesize that with this statement. But anyway, this is not my only problem. Sorry, before that, I think I have 4 more minutes. I want to say one more thing. So insisting on hollowness is useful because, technically useful, because I lied a little bit. I said that supersymmetry completely determines the quartic terms. In fact, I thought that is true, and I gave a talk at Aspen claiming that that is true about a year ago, and I gave the wrong action. For those of you who were at my Aspen talk, I apologize. I gave an incorrect action after I went home. I realized that I can add this term that is also supersymmetric, and that simplifies the action greatly to what I showed you today. So I can add that term times an undetermined coefficient. That supersymmetry is okay with that. I didn't write the fermions, but there's some fermion completion. So why not add it? Well, it's not hollow. Moreover, hollow, we can ask what happens at higher orders. How do I continue to to complete this action? I mean, if ultimately I would like to have an action that's also renormalizable. If maybe, I don't know, maybe that's too much to wish for in 6 dimensions, but there are a lot of things going for us. We have the self-duality protects the coupling renormalization, so maybe it is, I don't know. So how do we continue? I only did the calculation to this order. Well, hollowness also allows us to rule out higher orders because hollowness will require that for every box, every integral over the curve pole surface, there should be a partial derivative somewhere inside the box that will allow me to push the integral to the boundary. Whatever sits inside has to be a total derivative to be just an integral on the curve pole itself. The box has dimension of -2 because it's an area. It's an integral over an area of whatever fields sit inside. So what kind of terms can I have? First of all, let me just mention, obviously, all the terms that I have here are of dimension 6 because we're in 6 dimensions. Everything here is of dimension 6, if we count. So what kind of terms of dimension 6 can I have? Well, at the order where I have n fields, the structure of the supersymmetry is such that I would have n-2 boxes. At quadratic order, I had no boxes. At cubic order, I had 1 box. This is quartic order, and I have 2 boxes. With order n, I would have n-2 boxes, and they should come with n-2 partials somewhere inside. So they should be total derivatives. And that has dimension n+2, because the box has dimension -2. And the minimal dimension for a field in 6 dimensions that I can take is the scalar field of dimension 2. So altogether, these terms have dimension n+2. But for higher than quartic orders, this is bigger than 6. So basically, I'm pretty much done with by what I've shown you, except for the one annoying fact that I have to keep correcting the current order by order. What I wrote is the 0th order expression, wherever here the current, well, in the other formulas, the current is the 0th order one. I have to keep doing the nether prescription to correct it order by order. But it looks like that's it, if I can be guaranteed of hollowness. That's like we had here. That's possible, yeah. So that was a little bit glib, I agree. I mean, I can't think of how that would work because what happened before was because I already had that J current vector field interaction that needed to be fixed somehow. But you're right, I mean, I have no proof. There's another problem. I guess 0 minutes, right? So I'll be done. This is the last. So for hollowness, there was a field redefinition that I needed to do to make things work. And the field redefinition was lots of technical stuff, but it also has a chiral field dependent by this parameter rotation of the hypermultiplet fields. And the hypermultiplet field contains 2 chiral fermions of opposite charge, or opposite R symmetry charge, and they get rotated as well. And in 6 dimensions, opposite charge doesn't help us to cancel anomalies. So there is an anomaly here. There is a hollowness anomaly. And that anomaly would enter at order box to the 4. That is 4 boxes. The good thing is that these are abelian gauge fields, so this is a factorizable anomaly. So presumably a Green-Schwarz mechanism should fix it. In fact, there is a very natural Green-Schwarz term here because we have a B field. The formalism has built in a B field. Problem is that I don't quite know how it works because unlike the 10-dimensional Green-Schwarz mechanism or 6 other analogs in string theory, this field V is it's not an independent vector field, it's an effective field that was constructed from the B. So if I impose a gauge transformation on the B, that also affects the V. So there are extra terms. So I don't know what's going on here. I still haven't completed the calculations. It might be that the whole thing is anomalous. So let me just remind you that this V field is a field that's constructed out of the fundamental fields. So anyway, I'm going to finish here with open questions and then quick summary. So one open question is about higher. I haven't calculated anything beyond quartic order. I don't know if there are additional restrictions on sigma. This hollowness argument that I gave might suggest that this is all there is, but maybe that's wrong, as you just suggested. I don't know how to cancel the hollowness anomaly, but I think there's a potential for a Green-Schwarz because it's factorizable. And I don't know about quantum corrections, but there is a potential for it to be protected because at least once we settle the hollowness issue, as Jacques pointed out, then we know that the coupling is integral, the charge is integral, so it can't get quantum corrected, and maybe that's enough to protect the other corrections as well. Now, these are the field theory questions. Then there's the question, so how is all of that related to M theory in our poor M5 brane? In particular, is that really the theory that describes these low decup M5 brane in strong flux, or M5 brane in omega background, if you will, and which sigmas are realized? It kind of sounds like they should be the disks because that's what M2 branes would symmetrically want to expand to. Yeah, I'm going to skip all of that. I should say that, so this should also have some application to interactions induced by M5 brane and G flux. There's some other questions I have, more technical ones. Maybe pure spinor techniques can simplify the equations. I mean, I spent literally hundreds of pages of calculations because I did it the old-fashioned way, but the results turned out to be rather nice, so there must be a better way of doing the supersymmetry calculations. So let me finish here. So I suggested the construction for a supersymmetric action of interacting curvepoles, i.e. fixed-shaped strings, that seems to describe a sector that decouples of a low-energy sector induced on an M5 brane. There is a geometric constraint that we found on curvepole shape, and I have explicit formulas up to quartic interactions, and there are the other issues, and I'm going to end here and thank the organizers again.
I understand you talked about this type of equation from M in strong class.
Yes.
And one also think about at the end the result is basically 2-0
sorry, can you say that again?
I mean, in the end the result is 2, 0 and some other coupled to some loops.
Yes.
And one thing about this in terms of self-constraint, you try to couple like in the field of HV, you model and you try to couple one explicitly. One thing about this is trying to couple self-constraint to come as well.
Yeah, right. So if I understand the question correctly, this is actually one of my original motivations because, thinking about the 2,0 theory, let's think about it in the Coulomb branch, 2,0 A1 theory. So in the Coulomb branch, it should be a tensor multiplet interacting with whatever the W boson is. That W boson is maybe an M2 brane stretched between the 5 branes, so a string, but of course it's fluctuating and it seems uncontrollable what shape it takes. So maybe we can control the shape first as a first step, or as a poor man's version of the 2,0 theory, and then this construction suggests that there is a controlled way to just introduce these interacting membranes, but not let their shapes fluctuate all over. So, like I said, it seems like an answerable question, but I don't know what the answer is. I'm not sure if that was the question. I might have completely answered something else.
Because I'm asking about something completely different, probably from boundary problem, and arrive at some condition which should be imposed. I think I did also on the anomaly. Not the anomaly about which is a geometrical anomaly, but in general, one of the chiral field, H background, let's say anomaly F squared, for example. There's a similar thing for H squared, right? There will be some condition, but I don't know if we can derive that.
Oh, I didn't know that. Maybe I'll get the reference from you. Yeah, thank you.
All right, any further questions? Not that. Thank you again.
Thank you.